One of the really interesting things about the peaks that we get in NMR spectroscopy is that we can calculate the area under the absorption peak, right, and integrate that. And that can tell us the number of protons that generate the peak. Now, in modern instruments, the integration's done digitally, and the results can be displayed in a lot of different ways. One way to display the integration is as an integral trace superimposed on the spectrum. And that's shown by a blue line right here. So that's an integral trace. It resembles a stair step, and the size of that stair step is proportional to the total area under the peak. Because of this, the more the stair step of the integral trace rises for a particular signal, the greater the number of protons that contribute to that signal. Now, unfortunately, we do not have integration in our packet. So the spectra that I got, those real spectra, they're not going to have integration there. But you will run into a few in your book, your homework, where you'll see integration. And so let's look at this example. So this is 1,4-dimethylbenzene, also known as p-xylene. And we look at the integral trace that's shown in blue, and the signal at 2.3 here represents the 6 protons of this 2CH3. So this CH3 here and this CH3 here, okay? Then the signal here represents the protons that are part of the ring, so the 4 protons, 1, 2, 3, 4. So the ratio of these numbers is approximately 6 to 4, which we can then reduce down to 1.5 to 1, which is approximately the ratio of the distance of the stair steps. Often it's really convenient to convert the output from the integration into the smallest set of whole numbers, because the number of hydrogen atoms in each signal has to be a whole number, right? We're not going to get half a hydrogen. The actual number of hydrogen atoms in each signal is either the same as that in the ratio or a multiple of it. And so that tends not to be the end-all be-all, because while we know this spectra and it's we can say, look, that's 6 to 4, if that's the whole number ratio, it could also be, say, 12 to 8. Right, or 24 to 16. So these give us a ratio, but it's a reduced ratio. So just kind of be aware of that. Now, one of the most valuable tools that we're going to have is signal splitting. And we're going to talk about how to identify signal splitting, and then we are going to talk about why signals end up being split. So when we look at trichloroethane, and if we were to look at this, it would be Cl2H C CH2Cl. Okay, and so from what we learned in the previous screencast, we would say, look, there are 2 distinct protons here, so we should get 2 signals. What we notice, though, is that these signals aren't just one peak. They're these 2 peaks together, okay? This is called a doublet, and this is called a triplet. Now, these follow what we call the N+1 rule, okay? Now, in the N+1 rule, the protons that are next to each other are said to be coupled. So, protons, so let's talk about these coupled protons first. So protons that are coupled are chemically distinct from each other and are generally separated by 3 or fewer single bonds. Okay. And so what that means practically for us is that if a carbon, so if I have this proton here, which is attached to that carbon, it can be split by the protons on the carbon next door, the carbon that's attached to this carbon. Okay, now there's only one carbon attached to this carbon because we've got chlorines over here. Okay, so it is split by these protons here. And so the number of protons is the N. So the number of protons on the neighbor is N, okay? And so what this means is that on my neighbor there in purple, there are 2 protons. And so 2 plus 1 is 3, and we call that a triplet. And so what we see here first off is this carbon's attached to 2 chlorines, so it's going to have a higher part per million value, so we know and can identify it's going to be down here. And then what we see is also 3 peaks, so that is a triplet. In your packet, you are going to want to identify many of your protons based on their splitting patterns. It's a really versatile tool that you can use. Now, let's come over to this next example here, and we're going to look at these hydrogens. Now, so to look at these hydrogens, we've got to come over here and look at the next door neighbor. There's only 1 proton. So 1 plus 1 is 2, and that's a doublet. Okay? And so that's what we can see. That's how we can predict splitting patterns. Now, I'd like to do a few more examples before we go on to our next slide. So let's look at this one. We have CH3, CH2, Cl. And the first thing you need to do is you need to figure out how many signals are here. So when we look at this, there's no plane of symmetry, and we can see, like, look, this is the same distance away from the chlorine, and this is the same distance away, and this is a different distance away. So these are 2 distinct peaks. So first off, we know from this we are going to have 2 peaks. Right? That's what we know. And then the next thing we know is we can predict the splitting. So the splitting for this proton here, I'm going to come over and look at the number of hydrogens there, and there are 3. And so following the n plus 1 rule, that's going to be 3 plus 1, and so that gives me a quartet. Then for this one, I'm going to come over here and look at the number of protons on its next door neighbor. And so it's got 2. So that's 2 plus 1, and so that gives us 3, and so that's a triplet. Right? So we're going to end up with a triplet and a quartet in the spectra for this molecule. Now, let's look at another one. Let's do another example. Let's look at CH3, CH2C, double bond O, O, CH3. Now, there are no tricks here. There's no new information in this one. So if you wanted to, this would be a really good one to pause your screencast right now and then see if you can work through it and get the correct answers, okay? Because this is just an additional example problem for funsies. So let's say you've done that, and now we're checking our answers. Let's just go. We're going to have 3 distinct peaks because our protons are in different chemical environments. So for this one, I'm going to look next door. The protons next door, there are 2 of them. So that's going to be 2 plus 1. So that gives me 3. That's a triplet. This one here, I'm looking next door. That's going to be 3 plus 1. That's 4. That gives me a quartet. And then I'm looking over here, and this guy is attached to something that has no protons. So that's going to be 0 plus 1, and that's going to give me a singlet. Okay. Now, so that's what we could predict in our spectra. We can even go furthermore and predict, like, because this CH3 is attached to an oxygen and the oxygen's the most electronegative, I would expect the singlet to have the largest parts per million value, this to have the quartet to have the next largest parts per million value, and then this one to have the least amount of parts per million value. So we can use our knowledge of where the signals are going to show up, as well as the splitting patterns, to help us identify which protons are responsible for which peak. Now, maybe the burning question in your heart is, Dr. Pierce, we have really only looked at protons that only have one neighbor. What do you do if you have protons that have two neighbors? So, for example, look at that guy right there. He's got neighbors here and neighbors there. So what do we do about that? Well, what we do is we say we have to take both of those neighbors into account. And so I'm going to label this one A, and then this one B, and this one C. Okay? And so what you do is you take the number of protons on A and you add 1, and you multiply it by the number of protons on C, the other neighbor, and add 1. And so that's going to be 3 plus 1 times 2 plus 1, and that ends up being 4 times 3, and so we just call that a multiplet. Okay? Now, that's the only really unusual thing about this one, so you should be able to predict the splitting for the other two, A and C here. So when we look at this, it's going to be 2 plus 1, so that's 3. That's a triplet. And when we look at this one, that's going to be 2 plus 1, and that is also going to be 3, and that's going to be a triplet. Okay? And so this is how we can go around and predict the splitting. Now, if you're curious about where these names are coming from, singlet, doublet, triplet, quartet, quintet, multiplet, and so on, these are the common names that are given, and they're described right here. The number on the couple proton N, so if you don't have any on there, then your N plus 1 is going to be 1, right? And that's the relative peak height. One of the things that's interesting is that the peak heights can change, so you can get a pattern. So for example, on all those triplets that we saw, we would expect the pattern to be a 1 to 2 to 1. So where that central one is going to be taller than the other two at the sides. If you have a quartet, it's going to be a 1 to 3 to 3 to 1. So the way that this breaks apart, when you look at, and let me do that one first, right? So that would be boop, 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 like that. This one would be boop, 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 like that. Where these two are approximately the same size, and then these two are also the same size. Now, this is where I suck at this. This should be twice as big as that, and these should be this should be a third of the size as that. And let's just pretend like I did that. And then I'm not even going to try it with a quintet drawing it. If you want more practice, you're more than welcome to do that. I am not going to have you do that though. But that's what you should see, or those are the patterns that you should see. Now, you should also notice, and maybe this is the burning question in your heart, is that we have not messed with protons that are chemically equivalent. So what about those protons that are chemically equivalent? Well, they're kind of a pain. Because they do not show the effects of being coupled together, but you still have to use them for addition sometimes. And so let me first give you our first sentence here, which is chemically equivalent protons do not show the effects of being coupled together, right? So we're not going to see those signals being split. And he gives you this really complex example that I don't love. So I'm going to start out a little less complex. Let's look at this example. Cl, CH2, CH2, Cl. Now, at this stage, you should look at that and be able to tell this is just going to have one signal, right? There's a line of symmetry here. Those CH2s are chemically equivalent. So there's one signal. They're not going to be split by each other. So it's one signal and one peak because there are no other protons around. And so that's 0 plus 1, and that gives us singlet. Okay. Now, and we can see that here. When we look here, right, there's a line of symmetry there. We can also see a line of symmetry there. So the ones here that are chemically equivalent are this one, this one, this one, and this one. So those four are chemically equivalent. And then those two are chemically equivalent, right? And so what you see is you're not going to see any splitting with this particular example because of the resonance of the ring, and then the CH3s are separate. But I do want to draw your attention to this sucker. So if you have Br, CH2, 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 Br, okay? You should see here there's going to be some symmetry, and I'm going to label this as A. Nope. I want this to match my notes, otherwise things will go poorly. I'm going to label those protons as B, and this proton as A. Okay? Now, B is fairly straightforward. Those two B's are chemically equivalent, so what you're going to have there is just one signal for them, right? And you're going to look at the next door neighbor, it's 2 plus 1, and that's a triplet. Where we run into some interesting problems here is A, right? And what we find with A is that N is equal to the sum of equivalent hydrogen on each carbon. So if we look, we have 4 equivalent hydrogens there. So what we would do then is say 4 plus 1 equals 5. Okay, and so that's going to show up as a quintet. So let's do some more examples. Let's look at this problem. So this problem says an unknown compound produces a proton NMR spectrum that has just 2 signals. Okay, that's our first clue. We need to look for one with 2 signals, each of which is a singlet. So we've got to look at the ones that have 2 signals and the ones that are a singlet. So what I would like to do is identify the number of signals that we're going to see in each compound and the splitting. Now, my biggest suggestion for this is to make sure that you put all of your carbons and hydrogens in. Stick structures are great. They save us a lot of time. But the problem with that is that we can forget how many hydrogens are, say, in ring structures. Okay? It's just going to make this particular part a lot easier is if you are showing all your hydrogens. So let's look at this. The first thing I see here is we have a plane of symmetry. It's going to fall right through here. That means that these guys are going to be chemically equivalent, and then these guys here, those protons, are going to be chemically equivalent. When we look at this, that means there's going to be 2 signals, so it fulfills that first criteria, but the problem here is that both of these are going to be split, right? So A will be split and then B will be split, and they're going to be split in such a way where it's 4 plus 1, so both here are going to be quintets, which is not what we see, those are not going to be the singlets, so it can't be 1. So let's come over here to 2, and we have Cl, C, double bond O, CH2, CH3. And so when we look at this, we have A, right? And then we have B here. So we do have 2 signals, so that's the first criteria. But when we look at the splitting here, this is going to be 2 plus 1, so that's a triplet, so that's not helpful. And then this one here is going to be 3 plus 1, and so that's a quartet. And so that doesn't fulfill the requirements of 2 singlets. So let's look at this guy here, and I guess I'm going to draw him like below. And so if we look at him, it's CH3, C double bond O, CH2, CH2, C double bond O, and a CH3, okay? And what we see here is a line of symmetry here. We're going to have A and A here, and then B and B here, okay? Now, what's unique about these is both A and B are attached to a carbon that doesn't have any hydrogens on it. And so they will both lend themselves to singlets, because this one is going to be 0 plus 1, and that's going to be 0 plus 1. And so that's a singlet, and that's a singlet, right? And so 3 is the answer here. Okay. But just for funsies, we're going to go ahead and look at 4. When we look at 4, the very first thing we should notice is that this, and this are all chemically equivalent protons. So what you're going to end up with is just 1 signal, and there are no hydrogens on either of the carbons next to it, so it'll end up being a singlet. All right, and so 3 here is the answer. So that falls into that that criteria that the problem asked about. Now, maybe you're curious about why. Why do we have this n+1 rule? And so the origin of the n+1 rule can be understood by considering a lot of the magnetic fields, right, that are generated by a set of protons responsible for splitting a particular signal. So if we look at this particular signal here, right, what we see is that this proton, we're getting a doublet. So basically this proton is being split by this proton in red here. And so we can get 2 possible values for that local magnetic field. You can either have an alpha, which goes with the external magnetic field, or you can have a beta, which goes against the external magnetic field. And so that's why it appears as a doublet, okay, because you get these 2. When we look at triplets, all of a sudden, so this one can be up or down, right? And this one can be up or down. And so we can get 2 protons that are in the alpha form. We can get 1 proton in alpha and 1 in beta, right? And then we can get 2 in the beta form. And so these give us our 3 values, which is why we get triplets. And then we can have 4 values over here because we've got 1, 2, 3, right? And 3 plus 1 gives us 4. And so you can have 3 protons with alpha, 1 with alpha, right? And 2 a beta, 1 beta, 2 alpha, and 3 beta. And that is what gives us our 4 peaks there. So that's really where this is derived from. Now, one other thing that I want to point out is that if you have a nitrogen or an oxygen, you will generally not get any splitting from the protons on the carbon next to it. The reason we see this is there's a rapid proton exchange, and basically the protons on nitrogen and oxygen undergo some really extensive hydrogen bonding, and they just hop rapidly from one nitrogen and oxygen to another. And that's just much faster than what we can see in an NMR spectrum. So instead, what we're going to just say broadly is that NH2 protons are not coupled to any other protons, and neither are protons attached to an oxygen. So they're going to give broad signals that generally tend to have really, really low signals downfield. So you may not be able to even see these in your NMR. But that's why IR is so valuable, because IR would definitely show you an OH or an NH. So that's one of the reasons why NMR isn't the end-all be-all. We're going to use other spectra as well as NMR, particularly in our packets.